so that you can sit very naturally. Okay guys, let's go on to 5.2. In case you don't know what is 5.2, it's about circuits. And you have done circuits before. Okay? I hope that circuit is still inside your mind. It's still connected, it's not fragments of circuits. Okay, let's go for the basic rules first. Yeah, let's go for the basics. Series, and the other one is? Oh dear, parallel, yes, correct, parallel connection. Now, as the name suggests, series means that it is one after another, and there are certain rules that you need to follow. For rule number 1, VA equals to, what am I doing? VA plus VB. I'm doing 5.2 circuits now. No? And for rule number 2, it's IA equals to IB. Can anyone still remember what the rule behind this rule is? What's the principle behind this rule? Conservation of energy, yes, correct. And this one is conservation of? Why is it that the current flowing into one must be equal to current flowing into the other one? Because there must be conservation of? Sorry? Charges. Oh, the wise man. The wise man. And R effective is equals to RA plus RB. Easy, right? You connect things together, the resistance just increases. Easy. Let's talk about this. You got this one, this one, this one, and this one. So this is A, this is B. Rule number 1, VA equals to VB. 2, IA plus IB equals to I, where I is this one. Same thing. The reason why the two currents have to add up to be equal to the current over here is because of conservation of? No. Whatever things that flow over here must be equal to this and this, because there must be conservation of charge, correct. Whatever charge that flows here must be equal to the two charges added up together. Otherwise you destroy or create charge. And the world doesn't like it when you destroy charges. Okay? Now 3. 1 over R effective is equals to 1 over RA plus 1 over RB. Now I'm going to go a little bit deeper into derivation of these two and then derivation of something else. Now how do you derive these two? This one and this one. Let's take a look. Go back to fundamentals. Can you see that VA plus VB equals to E? Yep, this one is IA times RA plus IB times RB equals to I times R effective. And remember the current are the same? Ta-da, there you have it. Okay, let's take a look at this. Fundamentals using these two rules. IA plus IB equals to I, which is actually equals to VA upon RA, plus VB upon RB, which is equals to V upon R effective. Boom, boom, boom. The V are the same for parallel circuit, and that's why you get this expression over there. Okay, so this I don't think is mentioned. I don't think it's mentioned in the notes, so you might want to copy it somewhere. You will not be tested on derivation. I think that's too simple, but I think it's always good to know why things are the way they are, how it's linked to two fundamental ideas. So actually the only two rules that you need to remember are this one and this one. You can derive these two, but I would still recommend you to remember. Okay? Now let's go one level up to have you derive something more difficult. Let's call this VA. I'll just give you 2 minutes to just go through this mental storm to try to derive this expression over here. Give it a try. I'm going to use nothing else other than basic principles over here. Give it a shot. And I'll surface a very important idea behind usage of V equals to IR. Oh yeah, I have to assume that you know V equals to IR. Yeah, okay, good. How?
Right, but
it looks right? And then some people will say that by ratio lah. But what's the reason? What's the reason behind the ratio?
It's just math.
Math. The difference between math and physics is that physics is applied math.
That's right.
Yeah. So there must be a context. One more minute. Give it a try. One more minute. Derive this. Very useful formula. Very, very useful formula. Potential divider formula. Ready? V equals to IR. What R do I substitute over here? Yeah. There is a very important mantra that I want you to remember. When you use V equals to IR, it's very important thing that you must remember in order to avoid careless mistake is the V of the circuit, the I of the circuit, and the R of the circuit. When you use V equals to IR, you must remember the of what must be the same. The mistake that students usually make is that they substitute the wrong V for the wrong R or wrong I. So you must mentally just run through your mind, is this the correct, the V of X, I of X, and R of X. You need to run through this check. The problem is sometimes students just substitute V for X and then you put in R for Y. So mentally you need to run through. Can? And this will avoid a lot of careless mistakes. Cool. We'll run through examples later to reinforce this idea, but I just want to bring it out to you now. Why do I put RA? Because this is V of the whole circuit, I of the whole circuit, so R must be of the whole circuit. So I is equals to E upon RA plus RB. Let me use this again. VA equals to IA RA. V of A, I of A, R of A. So therefore this is equals to E upon RA plus RB, which is what you have over there. The ratio of the resistance. So the bigger the resistance, you always take away the more resistance, the bigger portion of resistance. The smaller the resistance, the smaller you take.
So when we use the fourth equation to derive.
You don't have to derive, you can use it directly. That's a good question. Yep, you can use it directly. Yeah.
You
Yep.
should test this derivation for this.
Oh, this is deep, man. Gosh. No, I think more of like I'll test you on like how to derive the resistance of something that looks like this.
That thing again?
Yeah, that thing again, yes, correct. Can?
E represents the D of the sun.
Yeah, the EMF of the battery. EMF of the battery. Can?
So is EMF different? It's different from voltage.
Excellent question. Since you asked, let's wait, give another 30 seconds. Then once everyone has reached this stage, then I'll explain the difference between EMF and PD. So that's why I was very careful in using PD or EMF, as you have noticed. There was a little bit pause, then I said EMF. There is a reason. Because you will be marked wrong if you say EMF of the resistor. You'll be marked wrong if you say PD of the battery. There is a difference. Okay? PD, potential difference. Yeah, you cannot say potential difference of the battery. You must say EMF of the battery.
Are you not trying to push anything through the battery?
One is giving energy, one is using energy. So it's fundamentally different. Okay, I think I sense that most of you are okay. So let's move on. I will go through this EMF, the difference between EMF and PD. EMF is defined as the work done by the source in driving unit charge through the whole circuit. Whereas PD is defined as the work done to drive unit charge between 2 points. So the main difference is this is 2 points, whole circuit, this is by source, this is through the device. Through whatever device you put in between the 2 points. Now if you're sharp enough, you'll notice that EMF can be equals to PD, right? Right? I mean, if your 2 points is just beside the battery, it can be, yes, and it is, indeed it is. If you sum up the PD over here, it is equals to the EMF. It is possible to be equal in value, but the definition is different. One is focused on the source and whole circuit. This one is between any 2 points. It can be even between these 2 points. Can?
Something by...
Which one? Is the work done by source in driving unit charge through the whole circuit. Whereas work done, PD is the work done to drive unit charge between 2 points. So it's a subset lah. PD is a subset. Yeah.
Okay, then between more than 2 points, what do you say?
Between more than 2 points, what do you mean? Say for example between...
We say we have component C, then between A and C.
Now if you have A, B, C, it's still PD.
Oh yeah.
So long as it is not the whole circuit, so let's say we have AD, AE, AE we still call it potential difference unless you're talking about the source. Then it will be EMF, yes.
The loads have a different definition.
Yeah, they say probably the amount energy converted from... Yeah, also can. Both definitions are fine. Amount energy converted from non-electrical to electrical per unit charge driven through the circuit is EMF. Then for the PD, it is the amount of energy converted from electrical to other forms. Also can. But if you are not sure, my advice is follow the notes in case of any dispute. Okay? This one also works. If you realize the definitions for both of them is based on this equation, V equals to W upon Q, which we did last lesson, right? It's based on this equation, V equals to work done per unit charge. But let me emphasize again, it will be wrong if you say PD of the battery. It is wrong, it is wrong. Yep. Almost like saying distance and displacement are the same, they're just different. But even the value can be the same.
Or can I say between the left side and right side of the source, there is no difference in potential source?
Oh, you're talking about potential now, not potential difference.
I mean,
between the left side and right side of the battery is?
There's no difference.
Cannot be, because battery, the purpose of having battery is, unless the battery is not working. If the battery is working, then you have, battery is like a pump. When you go through the pump, the water will come out definitely with more energy.
Oh.
So this side will have more energy than this side.
Okay.
Confirm. Yeah.
It makes no sense.
It makes no sense. Why have a battery? It's just a wire then. Actually, hang on. The electrons are pushed out from here, not that push out from here. It's the other side. This one has more energy than this. Question, since you're talking about this, why is it that we still define conventional current when we actually know that electrons are the one moving? Exactly. It is actually because of too lazy to change. Because before electrons was discovered, they thought that positive charges are the one moving. Remember I talked about how they define everything based on positive charges? Force per unit positive dash charge. Then they realized, oh dear, negative charges are the one that move. So how? They don't have internet, they don't have Instagram, they don't have Facebook then. So how do you communicate to the whole world? Everyone has adapted to that format for 50 years already. Now you want to change, you take another probably 10, 20 years to communicate to everyone. So it's okay lah. Let's stay lah. Let's stay lah. Life still goes on. Yeah, so then they add on another current.
Since you mentioned definition, is the part, when I define the force per unit
positive point charge, yeah.
Yeah, the small and the test. Is it necessary?
Okay lah. Actually, either point charge or test charge will do.
Or I mean to
yes.
say it's point.
Point, yeah, or test, yeah. If there is a preference, I will say point charge. IB prefers point charge.
What is non-point charge? I mean charge.
More point charge means extended. That means you got size. That means there's a significant size.
One charge can be extended.
Point charge versus extended charge. Point charge means it doesn't have volume.
And
negligible volume.
Is there any application of conventional current?
Actually, we always use conventional current. We always use conventional current, even though the actual electrons moving are this direction.
So even for like engineering and stuff,
they still use conventional current. Yes, correct. That's how powerful. How should I put it? That's how powerful laziness is. We know that it is not correct, but we still. Yeah lah. It's just like time. Do you know the actual definition of 1 second is actually 1 upon don't know 900, don't know how many thousand. Yeah, CZ pattern vibration. No. If you're going to say this every time, you're going to get so tired, man. But it's okay lah. We just time about there lah, about there. Yeah lah. So yeah, that's true lah. But just an analogy. Sometimes the accurate definition may not be the one that is convenient.
So even like
and
they just write it.
Yeah, they still use convention. Okay, let's try to derive something more difficult and challenging. Now, I will need you to try and derive this thing. IA, which is for this one, IA is equals to RB over RA plus RB times I.
I think it's the same step.
You try. Yeah. Yes, so try to derive this. Now you notice that if you want to find the current of A, you take the opposite one. You don't take the A. Unlike the V. V, you want to find PD of A, you've used PD A, RA as the numerator. This one, you want to find A, you use B. Which means something will happen because of the mathematics. The bigger resistor will take lesser current. The smaller the resistor will take the bigger current. Give it a try. Do it. Yeah. Do it. Follow it through. Yeah. The difficulty is not knowing, just knowing the solution. Is doing it and making it.
one of the express year 4 graduating courses. Like actually, so we need you down there, so.
Serious, that jialat.
Like I didn't get this for like so long.
Yeah.
Actually, I think now I understand because I got it already. But then this thing was like
Abstract. Yeah.
I don't know if there was a teacher or just me, but none of our class got it.
Serious. Okay, this is being recorded. I'll ask you certain questions after. Yeah, there's certain questions I want to ask, but I can't ask now. Yeah. But it's good that you get it now. And it could be the good work of the person who taught you previously.
It's kind of a hard concept. I mean, not hard concept.
That's why I personally never encourage this to be taught in year 2. I never encourage it. I think it's too difficult. Yeah, because it is actually a very difficult concept. You have to know energy, you have to know charges, you have to know a lot of forces involved. It's not easy. I'm a strong advocate of kinematics, forces, work done. These 3 fundamental concepts for year 1, 2. But no worries, you got it now. That's the most important thing.
It's not the teacher's fault.
I'm just standing on the shoulders of giant to help you understand. Can? So a test of understanding, would you like to derive it? Haha. It's not as easy as you think, right?
Yeah.
It's not as easy as you think. There's a reason why I do this the second, not the first.
I prefer just ratio.
Ratio. Makes sense, common sense, logic. Okay.
V equals to VB services.
Yep. Parallel circuit. Remember?
Oh, yeah. Oh.
Then you can get the expression right.
I use V total.
Yep. I've used nothing else other than this and this, which is those 2 over there. It's just that I elaborated it to here and then to here, and then do some substitution. And likewise, a response to a question that may come is that, do you have to prove this? No, you don't have to. You can use this. ASP paper, come on. You expect this kind of thing to come on ASP paper? Seriously? Prove V equals to IR, state Ohm's law. Come on.
It's very easy, like we just mess up A and B to left end.
Exactly. So what I want you to practice is the clarity of mind. Whenever you use an equation, what am I substituting? It's not just being careful. It's a habit of a physicist, a scientist's mind. Whatever you measure, whatever you find, are you clear about what are you finding? The mass of what? Mass of, mass measure from where? So the clarity of mind. Cool. We've got 10 more minutes. I'm going to, in a short while, once everyone is comfortable, then we'll move on to applying in real circuits. And I'm going to dive into the deep end of the pool. Because I'm sure that you'll be able to take it and not be short-circuited. Let's try. For those of you who are still here, continue, no worries. For those of you who are done and ready to take up the challenge, let's go.
Oh, mix.
Yes, correct, mix.
Very interesting. What's 1.5? I thought it's 1.95.
Find Rx, Ry. You'll be using some of the rules over there. Go ahead and try.
Is that for ohm?
Yeah, this is 4 ohms, correct.
Oh.
1.5.
Use whatever you can to find the answers.
I got x is 2.5.
2.5. Tell me I make a mistake. 2.5 cannot be what? You see, because this is 2.5. This is 2.5 m. So this is potential difference is 10 volts. So this potential difference is 8 volts. 8 divided by 4 is 2. It's 2. Yeah. I also got 2.5 but 2.5 m for 4 ohm. You see, this is 4 m over here. Do you agree that this must be 2.5 m? Because 4 minus 1.5 gives you 2.5, basic principle. So this is 10 volts. 2.5 times 4? 8. Because this plus this must be 18 volts. Yeah, but some students will think, hey, how come I don't take 10 plus 10, then take 10, 20 minus 18? No. The potential difference is across here. Yeah. You don't times 2. My brain hurts. Brain cramp. I'm shocked. Ha. Must know this, otherwise it will potentially make a difference in your grades.
This feels much better because it's O-level stuff.
It is. Relax. We will slowly move to the advanced stuff. Ready? If you are ready, those of you who have done this, take a look at this. Should I? Oh no. This one probably later. Find the effective resistance of this. Find the effective resistance of this. Yeah, it is. I'll start off with something you're familiar with, then we'll derive something that is of a higher order. A condition. We need to derive a condition. Otherwise you just remember situations. Huh?
Wait, sir, they are of equal resistance. It should be good.
Yeah, it is R. You must have gotten R by removing the one at the center. Why?
Because there's no difference, there's no potential difference.
Okay, good. What if I were to give you this noun? A, B, C, D. Derive a condition between the resistance of RA, RB, RC, RD such that you can remove X.
Such we can do what?
Such that you can remove X without affecting the effective resistance. No. No. RA equals to RB equals to RC equals to RD is a specific condition. They satisfy a general condition. So what's the general condition? Such that you can remove X without affecting the circuit at all. You're correct. The condition is that there's no potential difference. So what's the relationship between A, B, C and D such that the potential difference is 0?
RA over RB is RC.
RA over RB?
Because RC over RC.
Yeah, but how do you derive it?
Ratios.
Why? What's the fundamental concepts behind the ratios?
Because they affect voltage.
Yeah. Can you expand it so that you can also use it to practice your basic rules of circuits? Practice it, practice it. You're correct. You're in the right direction. Let's call this 1, 2, 1, 2, 3, 4. They're like collapsed. Zap. Okay, starting off from, do you agree that if V13 equals to V14, then it implies that V3 equals to V4? If the potential difference across V13 and V14 are the same, if the difference across them are the same, then the potential over here are the same. Agree? Can? Okay, so if you agree on this, then V13 using what you derived just now, V13 is actually equals to VA equals to VC. The potential difference across resistor A equals to potential difference across resistor C. Yeah, okay. So this one, remember that it is RA upon RA plus RB times the EMF of the battery must be equals to RC upon RC plus RD times EMF of the battery. Still alive? Still okay? Now this is the part where the one method is to make it, there's a method to make it simpler by flipping the whole thing around. So RA plus RB upon RA is equals to RC plus RD upon RC. Can you see that this is 1 plus RB upon RA equals to 1 plus RD upon RC? You strike off the 1, you get the condition. So the ratio of the resistance must be the same. So I can give you 2 ohm, 1 ohm and 6 ohm, 3 ohm. You can also remove the one at the center. Okay. Cool. You got the idea, huh? Okay. Now let's use the idea in a more complicated situation.
By the way, sir, for first case, I got
Kebab. Wait a minute. This is a star question. Ha. Star question. Okay, guess what I'm going to ask you? If each length you see here, has a resistance R, then okay, Hannah, what's the effective resistance across AB?
So what happened?
Yeah.
yeah, something that's
Something like that. Whoa! Holy! Wow! Wow! I sense a lot of resistance. Okay, people. It's almost time, and in fact, it's time. So I leave this question for you to think about. You have to use. Okay, a hint to you is one of the length can be removed, like this. It can be removed without affecting the resistance. The question is, which length? Think about this. There's a symmetry. If you look at it, there's a symmetry. Of course not. Small r is the resistance of each length that you see over here. Every segment that you see there has a resistance R.
But the segments are all different lengths.
You're correct. But let's assume that it is adjusted so that it is the same.
Oh.
It is adjusted.
So it's not a star, it's an argument.
We just, yeah.
For that question, right, what if the difference between 3 and 4 is different?
3 and 4?
Yeah, what if it's different?
Cannot be different because the thing is that if the resistance between the PD between 1 and 3 is the same as PD between 1 and 4, then the PD because this one is 0.
But what if the resistance is different?
Ah, right. If this ratio is not satisfied, that's what you're saying. Ah, then you learn in another lesson called Kirchhoff's law. They can use that law to derive. It's going to be complicated. It's going to be complicated, yes. That's another law too. Yeah, but you asked a very good question. What if it is not? This is a special case. Yeah, you're correct. You're correct.
It's not a common MCQ question.
Yes, correct. This is not common. This is common for ASP.
Oh.
Yeah, I love this question.
Can you
Then,
remove the horizontal?
then the higher order will be like, what if I connect this to, what if I connect this to? Yeah. Okay, people, I'll leave you to think about this. It's already time. And Ren, can you help me press the stop button? Yeah, just turn it around and press the stop. Thank you.